Okay, so in this module, we're going to see a crypto application of some of the operations that we've been discussing, including the partial trace, Ullmann's theorem, and the Schmidt decomposition. In particular, we saw that the Schmidt decomposition lets us decompose a pure bipartite state in a certain form that separates different degrees of freedom of the state into local degrees of freedoms that are used to describe the Schmidt basis and global degrees of freedom that are used to describe the Schmidt coefficients. So let's see an application of all these to the problem of secret sharing. So let me describe the problem first. So here's the setup. Imagine that there's a certain secret S, and for now we're going to focus on classical secrets. So let's think of this S as just being a bit, 0 or 1. And our goal is to distribute these secrets in between two parties, Alice and Bob, by sending each of them a share of the secret. So Alice is going to receive an A, Bob is going to receive a B, and the properties we'd like is that each of the parties by themselves is not able to recover any information about the secret. So Alice doesn't know S, even though she has A. Bob doesn't know S either, even though he has B. But if Alice and Bob come together and exchange their shares, A and B, then they're able to recover the secret S. So in this way, we've distributed the secret in between Alice and Bob. Each of them has a share, doesn't reveal them any information about the secret, but if you put the shares together, then you recover the secret. So that's why it's called secret sharing. Okay, so now let's pause for a second. How about you think of a scheme that lets you allow this? What's the idea? All right, here's one idea how to do it. Maybe I got the same as yours. One thing we could do is that use something that you saw a little bit earlier, which is one-time pad. So what's the way to use the one-time pad here? How does a one-time pad work? Well, we choose a key at random. Let's call this key A. So let's choose a random A from 0, 1. And then we take the parity of the message with the key. So let's set B to be equal to A plus S. So in this case, by the analysis of the one-time pad, we know that whatever S is, just because A was a random bit, B is random, uniformly distributed in 0, 1. So if I give A to Alice and B to Bob, these, from their point of view, just look like uniformly random bits. But if we put them together and we take the parity of A and B, we recover the secret S. So that's a classical secret sharing scheme. It works, it's perfectly secure, and it has the property that we're able to share one bit using two shares of 1 bit each. And so now what we're going to see is that you can do better using quantum states. So first, I want to introduce you a special basis of bipartite entangled states that's going to be useful for our scheme. This basis is called the Bell basis. So it's made of 4 states. These are 4 2-qubit states. I want to think of them as bipartite states shared between 2 systems, A and B. We could call them Alice and Bob. And this family of states has 2 important properties. First, as I already kind of leaked to you, it's a basis. So you can check that all the states are normalized. This is pretty clear. You can also check that all of them are orthogonal. So for instance, if I take the first state and the second state, they're orthogonal because they're supported on strings that are distinct. If I take the second and third states, now they both involve the same strings, 0, 1 and 1, 0, but there's a plus and a minus, and you can check that these 2 states are going to be orthogonal. Any 2 of these states are orthogonal. The dimension of the space is 4, so they form an orthonormal basis. It's different basis than the ones we're used to because it's not made of product states, it's made of entangled states, but it's a valid basis of C2, tensor C2. That's the first property. And now the second property is that these states are locally indistinguishable. What does it mean? Well, if I compute the reduced density matrix of each of them on either A or B, I'm always going to get the totally mixed state, half identity. For instance, we can do it for the first state. How do we compute the reduced density? We imagine measuring the B system. What basis are we going to choose? Well, it's natural to choose the computational basis. And if we measure B in the computational basis, then with probability half, A will be left in a 0, and with probability half, A will be left in a 1. So the reduced density, Rho A, is equal to half identity. And similarly, I could compute Rho B, which is also equal to half identity. We can do the exercise on any of these states. For instance, I could take the third state, I would again measure B in the computational basis, and observe that A is left in the totally mixed state. So the reduced density here are the same. And what does this mean? Well, we can apply Ullmann's theorem, which is going to say that for any two of these states, there is a local unitary that acts on A, and there is also a local unitary that acts only on B, and either or any of these two unitaries maps the one state to the other. For instance, if we're interested in going from the first state to the second state by acting only on the B system, there should be a way to do this because their reduced densities on A are the same. What's the way to do it here? We could apply a unitary UB which exchanges 0 and 1, right? So maps 0 to 1 and 1 to 0. We can do the same exercise in trying to go from the second to the third state, let's say by acting only on system A. This time, how would we do it? We need to map 0 to 0 and 1 to -1. And I'll let you find as an exercise the unitaries UA or UB that let you map the third state to the fourth state. Alright, so that's the two important properties of the Bell basis. Now let's use this basis to construct a secret sharing scheme. So I put the Bell basis for you in the upper right here so that you can keep it in mind. And now we're back to sharing our secret. Let's be more ambitious than in the first time round. Let's try to share a 2-bit secret now. So S will be 00, 01, 10, or 11. And we're going to share this classical secret using entangled states. So let me distribute the secret as a quantum state, phi s, that will be shared between Alice and Bob. And the properties that I want are exactly the same as before, given their share of the state, meaning given Alice can only has access to Rho A, Bob to Rho B, where Rho is the density matrix corresponding to my pure state phi s, so it's a rank 1 density matrix. So this Rho A and this Rho B, maybe I should put an S here, Rho SS, so Rho AS should not give any information about S, meaning that it should be independent of S. This one, Bob's, should also be independent of S, but it should be the case that the state phi S lets us recover S with probability 1. And what this means is that there should be a measurement that measures phi S to recover S, so these states phi S should be orthogonal for different S. Okay. How do we do this? Well, you know it, right? My notation has leaked it. I mean, I sort of told you already. The idea is simply to encode secret S using the Bell basis state phi S. And this satisfies all the properties that we need. We know that the 4 states are orthogonal, so they let us recover the secret S. But their reduced densities on A or B are the totally mixed states, so these never leak any information about S. So that's it. Now we've managed to encode 2 classical bits using 2 shares of only 1 qubit each. So this is a scheme that's twice as efficient as the classical scheme. Now, it has one drawback, which is not a problem in terms of a secret sharing scheme, but is something to keep in mind. We observed earlier that it's always possible to map from one of these Bell states to another by acting only locally. What this means is that even though Bob from his reduced density matrix has no information about the secret S, he can apply unitaries, let him switch in principle from one secret to the other. So Bob could apply a transformation to his system, use one of the unitaries UB, and that would change the secret. It wouldn't let him get any information about the secret, but it would change it. And in some applications, such as bit commitment, which is an application that you'll see much later in the course, this is a problem. But it's an unavoidable problem, right? Because it's a consequence of Ullmann's theorem. If we want Alice to have no information at all about the secret, it means her reduced density cannot depend on the secret. But if Alice's reduced density doesn't depend on the secret, and Bob holds a purification of the state, it must mean that there is a way for Bob to map state corresponding to a secret to the state corresponding to a different secret. Now, we've seen how to encode classical secrets in quantum states. How about encoding quantum secrets in quantum states? I'll let you think a little bit about this, and we'll see one way to do it in the next module.